everyone, welcome to lecture 12 of AREC 333. And today we will start with the economic aspect of production for two variable inputs. And the outline for today's lecture, here I listed profit maximization from two inputs. And again, like the one variable input case, we will start with the input perspective. And even though I listed profit max here, today we actually, before profit max, we actually need to do the cost minimization first. And before that, again, I will very quickly introduce the value and factor cost concepts for two inputs. And then we will do least cost combination, or sometimes called cost minimization. And from the result of that, we will be able to show what is the expansion path. For suggested ratings, usually I will say that Rasmussen is a little bit advanced for you guys, but this time I do recommend that you read Rasmussen chapter 4. For diverting, chapter 7 is more relevant for today's topic. However, chapter 6 is more general about optimization when there's two or more inputs. So that is actually kind of the content that we covered in lab 2. So I do recommend that you also, if you haven't watched the video for lab 2, then you should do so, because we're going to use some of the knowledge covered there. So let's go over the value and the factor cost concepts very quick. They are very similar to the one variable input case. However, let me make a little bit more explicit here is that when I say there's value concepts, for example, TVP, AVP, MPP, those are all from the input perspective. And from output perspective, you will have different concepts. Those include total cost, total revenue, marginal revenue, average revenue. So those are from output perspective. And again, for the input perspective, the costs are total factor cost, variable factor cost. So whenever possible, I will add factor there so that you are aware it's from the input perspective. So I hope that helps you to clarify the difference between input and output perspective. The first concept here is TVP for two variable input case, and I should put a parenthesis here. Sometimes I will just say two input case, but still you should interpret that as two variable input case. Why is that? Is because this production function is shorthand for this more complicated writing where x3 to xn are hold fixed. So this is, I do not want to write every time this long expression for the production function. So pay attention to that. So TVP for two input case are related to one input case in exactly the same way that TPP, APP, MPP for two input case are related to those concepts in one input case. Here, TVP is again the output price P times the level or the quantity of output, which is this production function. And the average value product, again, very similar to APP1 and APP2, but you just need to remember on the numerator, it should be TVP, not TPP anymore. So the marginal value product concept here is also similar, but I actually written out what MVP means. Again, just to make sure that you're understanding this concept very well. So MVP of an input, remember MVP is the input perspective concept. It is the exact rate of change. So rate of change is the slope or the derivative. And in AREC 333, we're always interested in the exact rate of change or point MVP, point MPP. So it is the rate of change of TVP resulting from infinite small change in that input. So for example, here MVP1 is the change in TVP with respect to X1 while holding all other factors constant. So this MVP is the change in TVP due to a very small change in X1 while holding X2 constant. And similar to MVP2, so when you have two or more inputs in your production function, then your interpretation of your marginal concepts should always be that it's a rate of change of something something holding the other factors constant. The total factor cost is this time, remember in the one input case, it's just Rx plus B. And B is the fixed cost, Rx are the variable factor cost. Here we have two inputs. So this is the price for input 1, and this is the price for input 2. So that's the only difference. The marginal factor cost, again, in the two variable input case, we have also two marginal factor costs. And again, I also written down what MFC measures here. And it's exactly the same wording as MVP. The only difference here is instead of TVP, here we're having TFC. So I think once you understand what marginal is, then it should be easy for you to understand the different marginal concepts. So one thing to notice here is that the MFC of total factor cost and MFC of variable factor costs are the same. So I should also put here variable factor cost over X1. Why is that? It's because variable factor total factor cost is equal to variable factor cost plus B. And if you take derivative of B with respect to either X1 or X2, then it's 0. So that's why the marginal factor cost is the same for either TFC or VFC. So again, similar to one input case, the marginal factor costs are constant here, which are just the input prices. In the one input case, when we're producing the output, there's only one to one mapping between the input and output. So for example, if we have a function, production function, y equals to x squared, and if our input is 1, then our output will be 1. And if our input is 2, then our output will be 4. And input is 3, output will be 9. So this is 1-to-1 relationship. However, in two variable input case, there are actually infinitely many different combinations of input to produce the same level of y. So this graph is actually the isoquant graph that we have been using for the recent several lectures. On the x axis is x1, and on the vertical axis is x2. So this is the relationship between x1 and x2. And again, each isoquant curve means that is the same level of y, so same level of output. And along the same isoquants, you can find infinitely many different combinations of x1 and x2 to produce the same level of y. So again, here you have to be clear that in two variable case, the difference between from one input case is that we have many different combinations of inputs. And in one input case, we don't need to choose the input used. However, here we actually, the producer has to decide which input combination to use. So intuitively, if the producer is constrained to produce a certain level of Y. So for example, let's say this is Y0 here. So this isoquant. If that is the level of output to produce, either because the producer signed a contract to supply a certain amount of output to a buyer or for other reasons, but let's assume that the producer has to produce this amount of output, then intuitively, in order to maximize profit, then the producer actually should find out the lowest possible cost for using the two inputs to produce that output. Maybe it's not intuitive to you, but maybe pause here and think a little bit. If you have to produce a certain level of output, then how are you going to choose your input? But at the end, we will show that in order to max profit, the cost minimization or least cost combination is a required condition. And there's actually one more condition to maximize profit, but we will not touch that and leave that for later on. So let's assume for whatever the reason, the objective of the producer is to produce a certain level of output. So when I say a certain level of output, that translates to the isoquant curve means that we are interested in one particular isoquant curve. And for that isoquant curve, let's assume that the output level is Y3. So the producer is trying to find a combination of input that will have the lowest cost, while at the same time produce that required Y3 level of output. And when we try to find out that input combination, we are actually solving a constraint, cost minimization problem. And when we solve that cost minimization problem for all given of at levels of output, so for example, for Y2, Y1 here, if we find out the combination for all levels of outputs, for example, let's assume for this output it's here, and for this level of output, the least cost combination is here, and for this output level, the least cost combination is here. Then if you connect all those least cost combination points, you actually get a expansion path. So here, expansion path is for all given levels of output, and if the producer is solving cost minimization problem, is actually working on one particular isoquant curve. Let's have a very quick overview of the constraint optimization problem. And I have to remind you, this is from lab 2. So if you are not familiar with this approach, you should go to lab 2 and watch the video there. So usually we will have the objective function. Those two are the decision variables here. We are having a maximization problem. We can also have a minimization problem, and there's a constraint there. And if we use actual production functions, and or here is a profit function, then here is what an actual constraint optimization problem look like. And the steps for solving this constraint optimization problem is using Lagrangian. And you have to first introduce a new variable, which is the Lagrange multiplier, and define a new function, the Lagrangian function. And then you set the partial derivatives of L with respect to all three of them equal to 0. Here, there's also a step 3, but in this course in AREC 3, you usually don't need to go to step 3 there. So again, those are how you set the partial derivatives of L with respect to those three variables. And I do want to emphasize here the Lagrangian multiplier. So you do need to understand what the economic interpretation of Lagrange multiplier. So again, I have an example of using profit there, and a little bit later we will explain, we will interpret Lagrangian multiplier in the cost minimization problem. And you usually don't need to compute the Lagrangian multiplier. However, you do, if I give you the Lagrangian multiplier value, you do need to know how to interpret that Lagrangian multiplier. Let's first formulate the cost minimization problem here for the two variable input case. So in the objective function, we have the total factor cost. Total factor cost, as I explained, this component is a variable input case, variable input cost, and this part is a fixed cost. And you will notice here a little bit later on that this B actually doesn't matter here, because once you're doing you're taking derivatives, then the derivative of B with respect to variables will equal to 0. But let's just write it here for completeness. So the objective of the producer is to minimize the total factor cost. The decision variables are the quantities to use, the quantities of the two inputs to use. And there's a constraint here. The producer has to produce this level of Y0, which is given, which is predetermined. And it has to be produced through this production technology described by the production function here. So again here, I want to emphasize again, this is the cost minimization for one isoquant. So there's only one output level here. And also we're not doing profit maximization yet. We're fixing our output level. Then for that output level, we're minimizing the cost. We're trying to find the least cost combination of inputs. And using the Lagrangian function methods, whenever we're having a constraint optimization problem, then we can write it this way. This part is just the objective function, which is the cost. And then we put this Lagrangian multiplier here, and inside this parenthesis is the constraint. And the constraint here is actually saying that you have to produce this Y0 level using your X1 and your X2. Once we have our problem set up, the actual solving process is simple. So we take derivatives of the Lagrangian function with respect to three variables here. Remember, the Lagrangian function is a function of not only x1 and x2, but also lambda here, which is a Lagrange multiplier. So taking partial derivative and set them equal to 0. Again, here we should check the second order conditions, but I don't think that's the focus of this course. So for this course, you don't actually need to do that. And that's the conditions for the cost minimization. And I do want you to notice here, if you take derivative or partial derivative of your production function with one input, then what you're getting here is your MPP there. So we can actually write this condition, this three condition, as here R1 equals to lambda MPP1, and here R2 is equal to lambda MPP2, and the last condition is Y0 equals to Fx1 and X2. Before I derive the condition for cost minimization, let me spend a little bit time here on this Lagrange multiplier lambda. So here, lambda is actually the marginal cost which is a output perspective concept. And why is that? So if you watch the video for lab 2, you will know that lambda should be mirroring how much your objective function value. Here, the objective function is cost. So here is how much cost will be increased if the output, which is y0 here. So if the output is increased by a small unit here, then what's the change in your cost? So your change in your cost with respect to your output level, and that is the definition of marginal cost. And we actually derived this condition R equals to MC times MPP in the one input case. So you should check lecture 9, and I think it's slide 4, where I summarized the link between the input and output perspective for one variable input case. And if you do check, this is true for the one input case, and if you compare those two conditions with this one input case condition, you will find this lambda here is equal to the marginal cost. So in the two input case, you just put a subscript there, and that become your one of your condition for cost minimization. So let's actually look at the several conditions, optimality conditions here. So here, if we divide, take the ratio of the input prices and also the ratio of the terms on the right-hand side of the first two conditions here, we can actually get R1 over R2 is equal to MPP1 over MPP2. And because this lambda is the same, so we can actually cancel that. And we ended up with this condition: the ratio of the input price is equal to the ratio of the marginal physical product. And there are several implications of this condition, and also several interpretations of this condition, and we should go over them in detail. Let's take a closer look at the optimality condition here. The ratio of the input prices is equal to the ratio of the MPPs. So the one interpretation here is that in order to minimize the costs, the producer should produce where the economic trade-off is equal to the technical trade-off. So the economic trade-off is the two input prices, whether you're using more of X1 or more of X2, and that the economic trade-off will be the input prices of those two inputs. And the technical trade-off, and remember again in this course, technical means the quantity, the physical quantity that's produced. And this is in comparison to economic. So the technical trade-off is between the two MPPs. So the marginal physical product of input 1 and the marginal physical product of input 2. So in order to minimize costs, the producer should choose to produce where the trade-off, the technical trade-off between those two inputs are exactly the same as the input price ratio. So I did mention there are more price ratios in this course, and here is another one. So, and if you still remember that the ratio of the two MPPs when we introduced the concept of RTS, or marginal rate of technical substitution, then this ratio is actually equal to the marginal rate of technical substitution. So again, this RTS is defined as the negative of the slope of X2 with respect to X1. So that is the negative of the slope of the isoquant. So for this isoquant at a specific point, the negative of that slope is equal to the ratio of the marginal physical product. So if you don't remember how we ended up with this relationship, you should probably go back to the lecture where we introduced the RTS concept. So the condition then is saying that the marginal rate of substitution is equal to the input price ratio. And this is another way that you can interpret the optimality condition. And here I do want to emphasize again that for this course, you should assume that we're working with a perfect competition in both factor and output markets. Then we're having this this optimality condition. When we do have time, we might be able to get to the case where there's imperfect competition in those two markets. But until we get there, you should assume that we're always working with perfect competition in those two markets. So that's both the economic interpretation of the optimality condition and the mass derivation of that condition. But let's also have a graphical interpretation of that condition so that you have a better understanding of this condition, because it's really important. So before that, we need to introduce one more concept here. So first is the variable factor cost that we have already mentioned is the input price times the quantity of the two input used, and then the summation of those two costs. Then we have to introduce a new concept here, which is ISO cost, or sometimes it's called budget line. And again, ISO means equal, and cost means cost. So this line is supposed to describe along that line, you're having the same cost. So how do we get there? We work with this variable factor cost equation, and we actually move the x2 term to the left of the equation, and that will equal to C minus R1 x1. Why do we move x2 to the left? Is because usually for the isoquant curve, x2 is on the vertical axis, so we do want to find a way to write x2 as a function of x1. Okay, so then divide both sides by by R2, and we ended up with this term. And if you further simplify it, this is the slope of the iso cost curve, because this is the term in front of x1, and this is a constant there that will be your intercept. So again, the slope of the iso cost line is the negative of the input ratio. In the graph, let's actually go a little bit slow here. Similar to the isoquant curve, you also have x2 on the vertical axis, x1 on the horizontal axis. And if you want to find out a particular iso cost line, because it's a linear function, so it's a line here, then where should you start? So you should start with this point. Suppose your cost is C1, and then since this is the x2 axis, the vertical axis, your x1 equal to 0. So when your x1 equal to 0, what is the quantity of x2 that you can afford with this C1? So this C1 over x2 will be the x2 quantity when x1 is equal to 0. So x1 equal to 0, x2 equal to that number. So that's a case when you spend all of your money on x2. And the other extreme case is where you spend all of your money on x1, and in that case, x2 equal to 0 and x1 equals to all the money, or here it's we can also call this a budget. So all of your budget spent on input 1. So 1 unit of x1 is R1, and the quantity of x1 that is allowed by this budget C1 is C1 over R1. So those are the two extreme cases. And then if you connect those two points, and any point along that ISO cost line can also be afforded or also having this cost of C1. So any combination along this line have the same cost. So those different combination of inputs are having same cost. So each line here is representing one cost. What's going to happen to the ISO cost curves if we change the input prices? So let's actually take a look here. This is what the ISO cost curves are like right now. And this is the input price, current input price for input 1 and the price for input 2. So if I change the R1 to make it smaller, so R1 smaller, you can say that the curves are becoming flatter. So why is that? If you actually pay attention here, if R1 is smaller, then this C1 over R1 point is larger. So let me actually go back. So this is what it was. And if R1 becomes smaller, then this value will move to the right. And at the same time, this C1 over R2 is constant. So that's why the curve is becoming flatter. And if we increase R1, then the curve is becoming becoming steeper. So and for R2, we can also say how will the slope of the curve change if we change R2. So if R2 is smaller, then R2 is smaller, C1 over R2 will become larger, and it will move to higher positions. So if we decrease R2, you can say that the ISO cost curve is becoming steep. And if we increase R2 value, then the curves are becoming flatter. So the slope of the ISO cost curves is decided by the ratio of R1 and R2. If you change each of these two input prices, then the slope will change. And I should also mention here, so assume this is C0, this is C1, C2, C3, then it's always true that this C1, so the cost or the budget represented by this ISO cost curve is larger than the cost or the budget represented by that ISO cost curve. So if you move to the northeast, then your costs are getting higher and higher, and your input yields in those two inputs are also getting higher. Now we understand what ISO costs are and what's the slope of the ISO cost curves, which is the negative of the input price ratio. And we also know from the definition of marginal rate of technical substitution, which is defined as a negative slope of the isoquant curve. So the slope of the isoquant curve is dx2 over dx1. Then from this condition, we can actually get the slope of the ISO cost curves are the same as the slope of the isoquant curves. Geographically, if you have the slope of a curve equal to the slope of a line, then they are tangent to each other. So here, the curve is the isoquant curve, and the line is the iso cost line. So our optimality condition tells us that the isoquant curve and the iso cost line should tangent to each other. So let's focus on this Y1 here. So the iso cost isoquant curve, that is for the output level of Y1, that's isoquant curve there. And the optimality condition is telling us in order to produce Y1, the least cost combination of inputs should be here at point C, where the slope of the isocost curve, the slope of the isoquant curve is the same as the slope of the isocost line. Pay attention here that the slope of the isocost lines are all the same as long as your R1 and R2 are fixed. So, and we can do a little bit of more explanation here what could happen. So in order to produce this Y1 level, we can also produce at either point A or point B. So those 2 points, or the input combinations represented by those 2 points, can be achieved by that isocost line. So that is C2. And again, we know that C2 is having a higher cost than C1. So you could produce at A and B. You could produce Y1. However, you do not want to produce at there, right? It's because if you move from A and B to point C, you actually ended up with a lower cost and same level of Y. So the producer always wants to produce at point C instead of point A and B. The optimality condition to the cost minimization problem tells us if we have a particular output level, for example, Y0, let's assume this is Y0, this is Y1, this is Y2, and this is Y3. So for each level of output, then we can find a point where the slope of the isoquant curve is the same as the slope of the isocost line. And then we find one solution to the cost minimization problem for that level of output. And if we move to a different output level, then we have to solve another problem and find the point where the isoquant and isocost are tangent to each other. And if we do this for all different levels of Y, and if we connect the locus of all those different cost minimization points or least cost points, then this green line here is what we call the expansion path. What I have shown you in the previous slide is actually the 2D expansion path. And here I can actually show you how does the expansion path look like in 3D. So this is 2 figures from BT et al. And on the left, we have the 3D expansion path, and on the right side, we have the 2D expansion path, which is what I have shown you before. So since the production function is a function of 2 input variables, and as we explained before, we will have the production surface. So we need a 3D graph to represent that production surface. And what that look like is that on the production surface, for example, if you prefix a output level, so that curve on the production surface means it's having the same level of output. And that if you project that output level to the X1 and the X2 plane, or the X1 and the X2 space, then you get that dashed line there. So that's your isoquant curve for this level of output. And you can also find another output level and project that onto the X1 and X2 space. You got that isocost curve there. So once you project those same level of Y curves onto the X1 and the X2 plane, then you want to find out the least cost combination of inputs. And now you work on the X1 and X2 plane. This is one iso cost curve, and this is another iso cost line, and that the slope of that line is decided by the two input prices. So those two lines translate here will be the C1 and the C2 here, and this one is this isoquant curve, and this one is this iso cost curve. And in the x1 and the x2 plane, the expansion path is a curve. However, in the 3D graph, the expansion path is actually along this production surface, and this line here is actually this curve on the surface projected to the x1 and x2 plane. So that's that curve there. So that's projected from the 3D production surface. So we usually don't work with the 3D graph, but I think it helps to understand where does this expansion path come from the production surface. Let's use an example here to illustrate the cost minimization problem. So here this is our cost function, and we are assuming the fixed cost is equal to 0. And you can tell from this cost function that the input price for input 1 for x1 is 3, and the price for input 2 or x2 is 6. And we are assuming that we have a Cobb-Douglas production function here. And if you remember the Cobb-Douglas production function form, we have 3 parameters, capital A, beta 1, and beta 2. In this example, A equal to 1, beta 1 equal to 1/3, beta 2 equal to 2/3. Before I even start the cost minimization problem, there's some information that you can tell from this Cobb-Douglas function is this is actually an overview of what we have learned before. This 1/3 is actually the factor elasticity for input 1, and this 2/3 is the, or I should say, the partial elasticity of production for input 2, and you can also say it's the factor elasticity for input 2. And we can tell more from this function is that the elasticity of scale is equal to 1/3 plus 2/3 equal to 1. So here, elasticity of scale equal to 1, then we're having a constant return to a scale. The reason that I mentioned this is because later on I will show you, because it's a constant return to a scale production function, which is a special type of homogeneous function, then we're gonna use the one of the properties of homogeneous functions. Let's actually solve this cost minimization problem here. So I will not go over all of those steps of setting up the Lagrangian and taking the partial derivative, set them equal to 0. What I will do here is I will use the optimality condition for cost minimization, which is the ratio of input prices equal to the ratio of the MPPs. So again, this is a very important condition, and I do hope you understand this condition very well. So the ratio of the input prices is simple here, so it's equal to 3/6 or 1/2, and we do need to calculate the MPPs. And let me actually do it here. So MPP1 is equal to partial derivative of the production function with respect to x1. And since we're taking derivative with respect to x1, then x2 can be considered as a constant. So it's equal to 1/3 times x1 to the power of minus 2/3. So this term here is because 1/3 minus 1 is equal to minus 2/3. And x2, we say it's a constant, so it's the same. And MPP MPP2 here is equal, again, the partial derivative. And this time is 2/3 here. X1 is treated as a constant here. X2 is minus 1/3. And MPP1 over MPP2 is equal to, we can just take the ratio there, and this 1/3 can be canceled, and those x1 and x2, the exponential terms, can also be simplified. So we ended up with 2, and here we have 1, and here on the numerator, we have x2, on the denominator we have x1. So the MPP ratios is just x2 over 2x1. And if we put it here, then we can actually solve x2 as a condition of x1. So x2 is equal to things here. They are the same. And we ended up with x2 equals to x1. So in order to minimize the cost of producing a given level of y, then we have to use x1 and x2 in the same ratio. Are we done here after we know that x1 and x2 should be used in the same quantity? No, actually. So we have to do one more step here, is plug this relationship into the production function. So assume that y0 is the output level that is given to us. Then we will have y0 equals to x1 to 1/3, and then x2, because it's equal to x1, then we also have it here, 2/3. So then y0 is equal to x1, and x2, because it's equal to x1, it's also equal to y0. So now we are done. We write x1 and x2 as a function of y0. Usually it's not as simple as this. X1 should be and x2 should be a function of the y level. Sorry, the 0 should be on the top. Then also r1 and r2 here, because of the parameters that I chosen, those are all canceled out. Graphically, this means that we choose the point here. This is the cost combination of x1 and x2, and if you draw dashed lines there, you will find out that the x1 and x2 are used the same quantity of x1 and x2 should be used. And if I give you this this problem, you can actually first draw the isoquant curve. And here I actually give a specific number for y level. So if you get that y level, this is actually our y0 here. And you can draw this isoquant curve. And since R1 and R2 are given, you can also draw a bunch of different isocost lines. And then you find out the isocost line, which is tangent to your isoquant curve, and the point of tangency is a solution to your cost minimization problem. I will stop here today, and next lecture I will explain to you what's the implication if you have a homogeneous function, what's the implication for the expansion path.